Georg Cantor and the Revolution of Set Theory. In 1870, when Europe was in a period of great technological and philosophical transformation, Georg Cantor, a young German mathematician, began his research on the real numbers. At first, what Cantor wanted to do was simply to organize these numbers in a strict and logical order. But what he discovered went far beyond his original goal, leading to fierce scientific debates and changing the way we understand mathematics forever. The beginning of the problem. The real numbers, including all integers, fractions, irrational numbers such as pi or 2. 2 are infinite. Infinity here is not just a vague concept, but an infinity that Cantor wanted to explore seriously. He wanted to answer a seemingly simple question: can we arrange all the real numbers in an orderly system? And if so, how can we choose any number from this set according to a well-defined rule? These seemingly simple questions lead to a paradox. The paradox of choice. Imagine you are faced with a set of real numbers. If you try to choose the smallest number after 1, you will quickly realize that it is impossible. After 1 there is 1,01, 1.01, then 1.1, 1.001, then 1.1, 1.1, and so on, never really following 1. This is the nature of real numbers. They are continuous, with no gaps between them. Cantor and set theory. Georg Cantor was not discouraged. He developed set theory, a new and powerful tool for dealing with infinities. In the process, he distinguished between different types of infinities: countable infinities, such as the set of integers, and uncountable infinities, such as the set of real numbers. This is where Cantor encountered a major hurdle. To understand the set of real numbers, he needed a new principle: the axiom of choice. This axiom states that in any set of non-empty sets, it is always possible to choose an element from each set, even if there is no explicit rule for making the choice. The great debate. The axiom of choice, though simple, sparked a fierce debate. Some mathematicians, such as David Hilbert, strongly supported it because it opened up important results in mathematics. Others, such as Henri Poincaré, objected, arguing that it was unrealistic and should not be accepted. Strange paradoxes began to appear. One of the most famous was the Banach-Tarski paradox. This paradox showed that if you accepted the axiom of choice, you could divide a sphere into a finite number of pieces, then reconstruct them to produce two identical spheres. The price of greatness. Georg Cantor was heavily criticized. Many of his contemporaries considered his theories illogical and almost a betrayal of traditional mathematics. The isolation from the scientific community took a serious toll on Cantor's mental health. He was hospitalized several times in his later years. But Cantor never lost faith in his work. He wrote, "My belief is that despite the paradoxes, mathematical truth always triumphs." Legacy. Today, the axiom of choice is one of the cornerstones of modern mathematics, used in a wide range of fields from real analysis to game theory. Cantor, despite his sufferings, left behind a great legacy. He opened the door to a new era of mathematics, where infinity was not just a philosophical concept, but a mathematical entity that could be studied, measured, and understood. Opposing infinities. Cantor's revolution. Since the dawn of mathematics, the concept of infinity has both amazed and puzzled people. For centuries, we have viewed infinity as a symbol of the infinite, something that is beyond our grasp. But in 1638, the great astronomer Galileo Galilei opened a new door to understanding infinity with a paradoxical conclusion. Galileo wondered, are there more natural numbers than square numbers whose square roots are integers? At first glance, the answer seems obvious. Square numbers become more sparse as we move up the number line. But Galileo realized that he could create a one-to-one mapping, where every natural number has a corresponding square number. And so, he declared that the two sets had the same size. From this, Galileo concluded that the concept of more or less did not apply to infinite sets. Galileo's view dominated mathematical thinking for centuries. Infinity was simply an abstract concept, with no distinction between infinite sets. But in 1874, Georg Cantor, a bold and visionary mathematician, asked the question, what if there were different infinities? Cantor started with a simple but bold idea. Compare the natural numbers and the real numbers between 0 and 1. If we could map these numbers perfectly to each other, that is, each natural number matched a unique real number, then they would have the same infinite size. But Cantor suspected that this could not be true. To prove it, he imagined an infinite list, where each natural number was matched to any real number. He then used a clever and revolutionary strategy, diagonalization. Cantor took the first decimal digit of the first number, the second decimal digit of the second number, and so on. He then changed each of these digits to create a new number. The result was that the new number differed from every other number in the list by at least one digit, and so could not belong to the list. This proved that there could not be a perfect mapping between the natural numbers and the real numbers. In other words, the set of real numbers is larger than the set of natural numbers, even though both are infinite. Cantor called the set of natural numbers and other equivalent sets countably infinite. But the set of real numbers, with its infinite complexity, belongs to a different kind of infinity, the uncountably infinite. This discovery shook the foundations of mathematics. However, the mathematical community at that time did not easily accept Cantor's result. Some called it a horror and even a serious disease of mathematics. But Cantor was not discouraged. He continued to develop set theory and expand the concept of infinity, leading mathematics into a new era. Today, Cantor's theory is not only accepted, but also forms the basis for many areas of modern mathematics. He proved that even in infinity, there is order and structure, and he left us with a profound lesson. Even the most impossible ideas can come true, if you are brave enough to explore. The story of Georg Cantor and his well-sorting theorem is a harrowing and challenging, but also memorable journey in the history of mathematics. Cantor, a famous German mathematician, revolutionized the theory of sets and infinities, but also endured many attacks from both the scientific community and his colleagues. The first step in Cantor's journey was the concept of good ordering. He wanted to prove that even uncountably infinite sets, such as the real numbers, could be arranged in a regular order. The question was, how could such an order be found in infinite sets? To answer, Cantor started with more easily understood sets, such as the natural numbers and integers. The natural numbers are clearly well ordered. The starting point is 1 and each of its subsets like 6, 7, 8, 8 can also be ordered in a clear way. But the problem began when Cantor thought about the integers. The integers extend infinitely in both positive and negative directions, which makes finding a starting point difficult. However, Cantor came up with an ingenious solution. By ordering the integers by their absolute value, first 0, then 1, minus 1, 2, minus 2, 3, minus 3, and so on. This allowed him to prove that the integers could also be counted and ordered in a good way. Although he had succeeded in sorting countably infinite sets, Cantor still had a bigger challenge: how to apply this principle to uncountably infinite sets, like the set of real numbers. He believed that any infinite set, not just countable sets, could be well ordered. This was an ambitious concept and, in the eyes of some of his contemporaries, a crazy claim. In fact, Cantor was unable to prove this, as every method he tried failed. But Cantor remained fiercely faithful to his work. He was a devout Lutheran, and he believed that his theory was a revelation from God. "My theory is as solid as a rock," he said. "Every arrow shot at it will quickly return to the archer." But Cantor's religious beliefs and overconfidence could not protect him from harsh criticism from the mathematical community. His former teacher, Leopold Kronecker, led a major attack on Cantor's work. Kronecker spoke out publicly, rejecting Cantor's entire theory and calling him a scientific fraud. These criticisms came not only from Kronecker, but also from many other mathematicians who did not believe in the validity of uncountably infinite sets. Faced with this ostracism, Cantor began to suffer from severe depression. He was hospitalized for a nervous breakdown, and for the next 15 years he taught philosophy and rarely returned to his mathematical work. However, Cantor's ordeal was not over. In 1904, at the International Congress of Mathematicians, Julius Koenig, a Hungarian professor, announced that he had proof that Cantor's well-sorting theorem was false. This was a major blow to Cantor's beliefs and career. But despite the setbacks and difficulties, Cantor's legacy lived on, and his work was later recognized as a great contribution to mathematics. Georg Cantor's life is a testament to his perseverance and belief in his theories. Despite constant criticism and hardship, although Cantor was unable to accomplish what he set out to do, his contributions to mathematics, especially in the theory of sets and infinities, remain an important part of the development of modern mathematics. The story of Zermelo and the axiom of choice is a classic example of mathematical controversies, where seemingly simple concepts can spark deep and lasting debate. This is a story about the development of set theory and how seemingly obvious discoveries can become the source of fierce debate within the mathematical community. The Zermelo controversy. One day, as Cantor, the founder of set theory, stood before a crowd of colleagues and family, he felt the heavy criticism of his work. The criticism came not only from scholars but also from his own family, and Cantor felt deeply humiliated. But in the crowd, there was one person quietly observing, a young German mathematician, Ernst Zermelo. Zermelo had been an admirer of Cantor's work. However, when he heard a lecture by Koenig, a colleague of Cantor's, Zermelo realized that something was wrong. Within a day, he had discovered a contradiction in Koenig's proof. After a month of intense work, Zermelo wrote a 3-page paper titled, "A Proof That Every Set Can Be Well Ordered." The paper was widely recognized for its perfection and the boldness of its approach. Cantor and the Problem of Choice. Cantor, despite his great achievements in set theory, was not fully aware of a crucial problem in his work. He had always assumed that it was possible to select an element from any set, even infinite sets, such as the set of real numbers, without needing an explicit mathematical rule for doing so. This was a key assumption in Cantor's theory, but it lacked a solid foundation from a theoretical mathematical point of view. Zermelo realized that this could not be accepted without an explicit axiom. He understood that there had to be a formal axiom to allow this choice in infinite sets, and it was this axiom that led him to develop his theory of the axiom of choice. Axiom of choice. The axiom of choice, as introduced by Zermelo, can be stated simply: if you have an infinite number of sets and each set is not empty, then there is a way to choose an element from each set. For finite sets, this seems obvious. You just go through each set and choose an element. However, when working with infinite sets, sometimes there is no natural rule for making the choice. In this case, the axiom of choice is necessary. Zermelo showed that although it is not possible to say exactly how to choose an element from each set, the axiom of choice allows us to assert that there is a way to make a choice from an infinite number of sets, including infinite sets. Applications in real number theory. So how can this axiom help with ordering real numbers? Zermelo used the axiom of choice to order real numbers. He chose a number from the set of real numbers, calling it zone, and then continued to choose other numbers from subsets of the set of real numbers minus the previously chosen numbers, forming a new sequence. This process may seem like Zermelo is choosing one number at a time, but in fact, the choices are made simultaneously from all possible subsets. Although the natural numbers are only countably infinite, Zermelo has shown that the real numbers can be ordered without contradiction, controversy, and consensus. Although Zermelo had provided a solid way to organize the real numbers, incorporating the axiom of choice into the formal theory was not easy. The axiom, while it solved many problems, was not easily accepted by the mathematical community. Some criticized its use, arguing that the idea of invisible selection of elements from an infinite number of sets was unintuitive, and that many mathematicians had used it informally for many years without realizing it. The main objection was that the axiom of choice seemed unimaginative, and so it was not easily accepted by many in the mathematical community. However, it was Zermelo who formalized the axiom, and it became an integral part of set theory. The story begins with an axiom in mathematics called the axiom of choice, one of the most fundamental yet controversial principles. It simply states, if you have an infinitely large set of non-empty subsets, then you can choose an element from each of those subsets. However, problems begin to arise when mathematicians ask, can something exist if we can't actually construct it? The appearance of contradictions. While this axiom is powerful and convenient in many ways, it raises difficult questions about how we understand and apply the concept of existence in mathematics. Many mathematicians assume that any proof must have a finite number of specific steps, but the axiom of choice often requires an infinite number of steps. While some may accept infinity in mathematics, they only allow countable infinity, not uncountable infinity, as the axiom suggests. When mathematicians began to play with the axiom of choice, we saw results that made them reconsider basic assumptions. One of the most disturbing results came from a problem by Giuseppe Vitali in 1905. Constructing the Vitali set. Vitali used the axiom of choice to create a set of real numbers between 0 and 1, but in a way that we cannot understand using common sense. He started by dividing every real number between 0 and 1 into an infinite number of bins, subsets. Each of these bins would contain real numbers that had a special similarity. If the difference between two numbers was rational i.e., could be expressed as a fraction, then they would belong in the same bin. This means that if you subtract 1/2 from 3/4, you would get 1/4 and 3/4, and 1/2 would be in the same bin. The rational numbers between 0 and 1 would all be in the same bucket, while the irrational numbers, like the square root of 2, would not belong in any bucket if they were irrationally different from the other numbers. The infiniteness of selection. Vitali uses the axiom of selection to select a representative element from each bucket. Since the axiom does not require us to know exactly what the element is, only that it exists, we can have a set of representative elements forming a Vitali group. Vitali then proceeds to make infinite copies of this set and shift each representative number by adding a rational number. This will result in each representative number appearing in every other position between 0 and 1, creating a non-overlapping set that covers the entire range. The problem with the size of the Vitali set. The problem arises when we ask ourselves what the size of the Vitali set is. We know that this set must contain all the real numbers between 0 and 1, so it must be at least 1 in size. However, since each element can be shifted an infinite number of times, could its size be 3, or could it be infinite? Curiously, there is no number that, when added infinitely many times, will have a value between 1 and 3. If the size of the Vitali set is 0, you can add it infinitely and still get 0. If the size is a small positive value, when added infinitely many times, you will reach infinity, not 3. This creates a major contradiction in how we measure the size of this set, the immeasurable set. Finally, we have to accept that the Vitali set is not measurable with the usual mathematical tools. It has no length, area, or probability. Yet mathematics is built on the idea that everything is measurable, be it distance, time, or weight. But now, with the existence of unmeasurable sets, the question arises, do we really understand all the basic mathematical concepts as we think? The Banach-Tarski paradox, a controversial journey of science. In 1924, at a small gathering at a European mathematics conference, two brilliant mathematicians, Stefan Banach and Alfred Tarski, announced a discovery that immediately caused a wave of controversy. It was not only a mathematical theory, but also a major challenge to human intuition and traditional physical ideas. Shocking revelation. Banach and Tarski claimed that if you had a perfectly solid ball, you could divide it into 5 pieces in special ways. Then, by rotating and moving those pieces skillfully, you could reassemble them into 2 balls that were identical in size and volume to the original ball. Not only that, they asserted that this process could be repeated indefinitely, creating an infinite number of balls from a single ball. This result, known as the Banach-Tarski paradox, quickly became a hot topic of discussion. Scientific background. The paradox is based on the axiom of choice in mathematics, another controversial concept that builds on set theory. The axiom of choice allows you to choose one element from each of an infinite set of sets, even if you can't specify how to do it. By combining this axiom with properties of infinite sets and measurements in 3-dimensional space, Banach and Tarski proved their theory. However, it is important to emphasize that the pieces being split are not ordinary physical objects. Instead, they are non-intuitive sets of points that have no physical concept of size, mass, or position. Scientific community reaction. The discovery was met with immediate opposition. Physicists consider it completely impossible in practice because it contradicts the laws of conservation of energy and mass. Others believe that this paradox is just an intellectual game with no practical application. However, in the world of mathematics, Banach-Tarski is seen as a profound demonstration of the power and limits of theoretical thinking. It forces people to confront a fundamental question. Does mathematics really reflect the physical world? Or is it just an abstract structure in itself? Academic journey. Despite being heavily criticized, this theory has strongly inspired research on non-Euclidean spaces, group theory, and infinite structures. In an interview late in his life, Tarski shared, "We did not create paradoxes to challenge physics, but to show the magic and sometimes the incomprehensibility of mathematics." But the story does not end there. In the decades that followed, the Banach-Tarski paradox was used as an example to discuss the nature of infinity in many different fields, from philosophy to computers to art, a wider impact. The paradox also highlights the limitations of mathematics when applied to reality. While it can be rigorously proven on paper, it cannot happen in reality because physical objects are bound by the fundamental laws of the universe. However, this does not diminish the appeal of the Banach-Tarski paradox. Instead, it has become a symbol of the magic and endless potential of mathematical thinking. From a simple ball, mathematicians have created a rich universe of ideas, axioms, and paradoxes. The story of a mathematical war. In 1930, in a dusty room at the University of Vienna, Karl Tarski, a young, enthusiastic mathematician, sat writing the final lines of a revolutionary research manuscript. The title was "The Axiom of Choice and the Nature of Infinity." The problem he was tackling was not simply a mathematical problem, but a profound metaphysical question. Is choice self-evident, or is it just an illusion of the human mind? The first encounter. Tarski sent the article to a prestigious journal in Paris, hoping it would be a turning point in his career. But the first response from the famous editor Lebesgue stunned him. No one cares about the equivalence of two false statements. The hurt came not only from the rejection, but also from the way Lebesgue completely dismissed the work. But Tarski was not about to give up. He resubmitted the paper to Fréchet, another editor, known for his open-mindedness. The response this time was the complete opposite. No one cares about the equivalence of two self-evidently true statements. The crisis. Tarski felt like he was caught in a paradoxical spiral. Two leading mathematicians, analyzing the same paper, had come to completely opposite conclusions. This was more than a difference of opinion. It was emblematic of a deeper crisis in the world of mathematics. When he shared this at a conference, the public reaction was mixed. Supporters of the axiom of choice believed it was a cosmological truism. Opponents said it was a philosophical hoax. This is unfathomable. It's like the Vitalis set. You can't work with it without destroying the nature of dimension. The debate became more heated when some young mathematicians began to scoff. If you believe in the axiom of choice, you might as well believe that we can split a ball into infinitely many pieces and put them back together to make two identical balls. Enlightenment and confrontation. In 1938, the decades-long silence was broken by an Austrian mathematician named Kurt Gödel. Gödel, in his genius, proved that there was a world where the axiom of choice was true. But he also emphasized that this was not a necessary proof. It was just a possibility. 25 years later, Paul Cohen went further. He proved that there was another world where the axiom of choice was false. This result not only opened a new era in mathematics, but also poured cold water on both sides of the argument. The mathematical community was deeply divided. Conferences became battlefields of words. A young mathematician said with irony at a major conference, "This is not mathematics, this is theology. We are arguing about things that no one can verify." Reluctant acceptance. Gradually, the ideas of Gödel and Cohen became the basis for a more pragmatic view. The axiom of choice is neither true nor false. It is simply a choice. Tarski, now a renowned mathematician, looked back on the years of debate and said to an old friend, "They were right. This was not mathematics. It was a game. But it was through that game that we understood that infinity is not just a concept. It is a reality that we will never fully grasp. And so, the paradox of the axiom of choice becomes a symbol of the ambiguity of human thought, where both right and wrong can coexist in a reality more complex than we ever imagined. The controversy over the axiom of choice was one of those defining moments in the history of mathematics, opening up profound debates about the freedom of choice and the limits of fundamental principles. Although the axiom has been widely accepted in the modern mathematical community, its acceptance and understanding has been far from straightforward and has been accompanied by an interesting reframing of how we view the geometric world. The four basic axioms of geometry are the foundation, the minimal rules that allow anyone to play the game. Without them, we have nothing to build geometric spaces on. But it is the fifth axiom, the choice of how we define parallel lines, that changes everything. If you choose that there are no parallel lines, you are playing in the space of spherical geometry, a curved space where everything changes in the way we understand distance and position. If you choose that there is only one parallel line, you are in plane geometry, where anything can be drawn on a plane without distortion. And if you choose more than one parallel line, you enter the world of hyperbolic geometry, where parallel lines cannot touch, producing results that defy all common intuition. But then comes the axiom of choice. This is the so-called mathematical universe that you can choose from. If you accept this axiom, you are not simply working with a set of specific principles, but with a powerful tool that allows you to make infinite choices without having to specify each step. This is a powerful theoretical choice that helps mathematicians solve unfathomable problems, reducing complex proofs to just a few lines. But this axiom cannot be proven or disproved completely from the other axioms. Indeed, there is no clear proof of its truth or falsity. And so mathematicians are faced with a major problem. They must decide whether to use it or not. From a set theoretic point of view, the axiom of choice cannot be disproved without shaking the entire foundation of the theory. This makes it an indispensable part of many important proofs and theorems. Paul Cohen, a giant in mathematics, proved that the axiom of choice cannot be proved or disproved from other axioms. His work in the 1960s helped resolve one of the longest-standing controversies in mathematics, and earned him the Fields Medal just 3 years later. Cohen's work, along with Kurt Gödel's earlier discoveries, led to a change in the way mathematicians viewed choice. The debate over the axiom of choice has died down, not because it is no longer important, but because mathematicians understand that mathematics can still develop with or without it. However, the real question has never been whether the axiom of choice is true. The more important question is, what is the axiom of choice good for? Does it help you understand theorems and relationships in mathematics better? Or is it simply a useful tool to reduce the complexity of proofs, like replacing a long-winded solution with a simple and concise equation? The answer, in fact, depends on your goals in applying mathematics. If you are a mathematician seeking convenience and efficiency in proofs, the axiom of choice is the most powerful tool. If you seek clarity and detail in every step, you may want to experiment in a world without it. Interestingly, some mathematicians still feel that proofs without the axiom of choice, although more difficult, give them a deeper understanding of the nature of infinite problems. There is ongoing research into universes without the axiom of choice, and this research is expanding the scope of mathematical theory. But regardless, the axiom of choice cannot be completely dismissed, as it has become an integral part of many modern proofs. Ultimately, if you remove the axiom of choice, you will find that mathematics becomes much more difficult. Progress in set theory, geometry, and many other areas will slow down, and problems that were once easy to solve will become exponentially more difficult. Choice is not something that can be easily ignored in the modern world of mathematics. It is the foundation of many important proofs, and those who ignore it may find themselves working with their hands tied behind their backs. So the important question is not whether the axiom of choice is true, but are you free enough to choose it in your own mathematical universe?